Everyone. Okay, so in this talk, we're going to discuss neural networks that process essential data structure, which is called a point cloud. A point cloud is a finite collection of points in space. We're first going to discuss why we would like to process structure, and we will survey some existing architectures process point clouds. And we will show that they have vulnerabilities. And then we will present new results that remedy. Okay, so let's begin with the background. So a point cloud is a very simple data structure. It's just endpoints in R3. So the way we receive this is matrix. And as you can see in the picture, at home you probably see it more fully. Here we see half a bunny, but we can receive physical phenomena in the form of a point cloud. For example, this bunny right here on the left is a point cloud, but it looks very similar to real life bunny because the points are very dense. And this allows us to construct a continuous mesh of this physical phenomenon in a way that's much more efficient in actually receiving a continuous manifold. Right, and when we work with point clouds, we also want to take into account certain symmetries. So for example, classifying a bunny does not matter if you rotate it, change the order of the points in this point cloud, it's going to remain the same classification. So we want to identify point clouds up to orthogonal actions and permutations, meaning that when we get 2 point clouds, so 2 matrices in R3, we want to say they're isomorphic. If there exists a permutation, rotation and reflection that takes one. Also, we might want to consider translation as well, but this is pretty simple. We can just center the point cloud by moving it to its average position, and then we just take care of it. Very good. Okay, so now we want to process this data structure using machine learning. The basis of all machine learning are neural networks. So what is a neural network? It's a finite composition, linear and pointwise nonlinear groups. So the entire function is just a linear function composed usually with ReLU by pointwise. So it's just the maximum between 0 and x. And it's a very simple function. We can write it just looks like this. This work? Marker? No. So it's just the maximum between 0 and x. It's a very simple function. And these networks allow for very efficient optimization of the parameter space. That's why they're used. And also, pretty surprisingly, this very restricted class of continuous functions are able to approximate any continuous function in a compact set. Thank you for taking the time. Okay. Very good. So this is ReLU. So this is x equals 0. So, and this is applying pointwise on the vector. So what's written here is M1. M1 gives me a vector, and then I apply ReLU to each one of the entries in. So this very simple construction actually yields a very robust approximator. We're going to use this to study the process. And not only us, a lot of people do. It works very well in practice. Okay, so the practical motivations for using neural networks to study point clouds is a very fast computation time. So in a very groundbreaking seminal work by Gilmer et al., they introduced a message passing neural network paradigm, which we're going to get into later in the talk. But essentially, they process point clouds using neural networks, and they achieved a 10 to the 5-fold improvement over density functional theory approaches, and yet still maintaining the accuracy on all of the molecular property benchmarks. And so this was a very big paper that really turned the attention of a lot of researchers into point clouds and using networks. Later in the talk, we're going to talk about the vulnerabilities of this class of architectures and how we fix it. Another interesting motivation that rose also lately is self-driving cars. So when you have a self-driving car, you have this radar-like device on the roof of the car, and it's called a LiDAR. It kind of spins around and sweeps images of surroundings. And the images that it receives are actually point clouds, not receive some type of a video information. And what we can do is we can map these point clouds and then use machine learning to process them and get a high definition map of the environment. So in this way, we get a computationally faster approach of processing information, which allows for kind of self-driving and actually implementing it in practice with latent times that are reasonable. If someone jumps on the road, you want to have a quick map of what's going on, and this allows for this quick information processing. Looking at information is going on. Okay, so now we're gonna get into theory a bit. So how do we process point clouds using neural networks? Okay, so neural networks don't process geometric information. There is no invariance respecting structure inside a neural network. If I take an object and I translate it, fit into a neural network, the output is going to be different. So how do we remedy this problem? We can actually identify point clouds up to orthogonal action by looking at their Graham matrix. So the Graham matrix is just x prime with x. This is going to be a matrix in R n times n. And this is known from invariant theory to be a complete descriptor of a matrix up to orthogonal action. So what does this mean? It means that if two matrices are mapped to the same Graham matrix, there exists some orthogonal action that takes one to the other. But what the problem is with this definition is that it does not account for symmetry stuff. Because point clouds also have permutation symmetry. So for instance, if I apply a permutation onto M and I compare its Graham matrix to that of N, it's going to be different, even though we would like to identify them identical. And if you remember back at the picture of the rabbits, we don't care how we order the points in this picture. Just looks like a rabbit. We want to classify it. And right, so this Graham matrix is very reminiscent of type of an adjacency matrix, right? So it's kind of an adjacency matrix graph with pairwise continuous features. So in regular graphs, we can describe any graph using a binary matrix. So we just have a matrix of zeros and ones. If a node is connected to another, we put the 1. If it's not, then it's 0. In this setting, what we do is we put between each two nodes, their projections onto one another. And we have some type of weighted graph, and we feed this into the. Right, so here we see an example of what it looks like. So on the right, we have some point cloud. Point cloud is the 6 points of red. And we can represent this point cloud up to some symmetries as a distance matrix. And this distance matrix captures all of the information of the point cloud up to translations and orthogonal actions. And the way the neural networks are going to work is it's going to process this distance matrix rather than the actual geometric information that is not invariant to orthogonal action.
Yes. Distance remain how many nodes?
No, so right, that's a good question. So what we're going to look at, this matrix kind of describes a complete graph. So all the nodes are connected to all the other nodes. And on each edge is decorated with a distance. So all the nodes are connected. And we just decorate each edge with a distance information. Yeah. What is the feeding distance? Yeah.
It's a weighted graph.
Exactly. It's a weighted graph with distance information on your edge.
So you can have a graph.
Yes.
Graph 3 with those edges will be in distance. And you will have shaded.
If you're giving me this distance matrix, I can recover this point cloud 1-to-1 up to symmetry. Great. Yeah, it's a good clarification. Okay, so now we're going to discuss the popular architecture we discussed for processing molecular input. So these are called message passing neural networks. They process graph. So let G be a graph. MPNNs operate on G when it is endowed with node and edge features denoted by XV and EVW. Like we discussed now, it's usually going to be distances. So the forward path of this network consists of two phases: message passing phase, and there is a readout. The message passing phase runs for predetermined iterations and is defined in terms of message passing functions and update functions. And so how is this done? We receive some type of graph, right? To initialize each node in the graph, the hidden states, which is just some vector with randomly initialized. And then during the message passing phase, we iteratively update this hidden state according to the messages received. So formally, it looks like this. So equation 1 describes the messages. So for each node P, we aggregate all of the messages coming from neighboring graphs. These are the neighbors of the graph. And then we apply some message function to both the hidden state of the receiving node P and to the neighboring node W. And we also pass some edge information. In our case, it's going to be. And then we update the hidden state according to an update function that receives messages and receives the current hidden state. And so essentially, each node has access to its distances from all of the other nodes in the graph, and then updates some hidden representation that we're going to use to classify things. Right. So, like I described verbally, each hidden state is going to attain some value after the iterations, and then to obtain a global graph feature, we're just going to define some permutation invariant aggregator and get a global feature for the graph. This is going to be the label. Earlier, we see a rabbit. This is going to be a rabbit. Classify something else. This is going to be the classification. Right. So this, what we described here, like all of we did not define explicitly the readout function, aggregation functions. This describes a general framework that's used by many models, such as SCHNet and GNN. And it's very indicative to look at this model and to find its problem because a lot of other models rely on the same character. Okay, so now, how do we analyze the expressivity of these models? We do this by a graph isomorphism test. And so like we said earlier, a point cloud is essentially a graph. So we want to know how expressive message traffic neural networks are in terms of graph isomorphism. So let's describe the Weisfeiler-Leman test, very famous graph isomorphism test. Computer science is pretty much ubiquitous when processing graph. So we feed this test a graph. We initialize a uniform coloring for all the nodes in the graph. And then we update a coloring of each node and by hashing its current color and the color of the set of its neighbors, and then updating its color to the next iteration timestamp. And we want hash to be an injective mapping set. And then similarly to MPNNs, we apply some readout function that looks at all the colors and outputs a hashing of this set of colors. This is going to be a global graph color. So this is how Weisfeiler-Leman process regular combinatorial graphs without any edge weights. It's just zeros and ones if they're connected or not. In our setting, it has been suggested by Kozniakov that we can also add distance information inside the aggregation of the neighboring colors, and this is defined as Weisfeiler-Leman for a geometric. Any questions? So what we're going to do is we're going to use this, and we're going to think about how expressive this test actually is. We're going to later discuss what type of point clouds can distinguish and what point clouds cannot. And before that, we just look at what it looks like in practice. So, like we described, we have some uniform Asian coloring, and then each node's coloring is updated by its neighbors, right? So this node has 3 neighbors, so it's colored differently than this one that has 2 neighbors, and so forth. And then this test kind of stops to reach coloring. It's not. So here there is no update coloring, so the test stops, and then we have a readout of the graph histogram. And 2 graphs are isomorphic if their coloring histogram are. Okay, so we want to analyze the expressive power of this test when applied, Weisfeiler-Leman test when applied to point. So let's begin with defining some basic definitions that will help us later on. So for a point cloud, we define the geometric degree of the ith node as the set of unordered distances from this point to all of the other nodes. And then we define the geometric degree histogram as the set of all of these geometric degrees. So what we have here is essentially a set of sets, where each one has all of the distances from one point to the other. Now we want to analyze the expressivity of this information. What does this information give us? So if we know that if we have 2 histograms or 2 point clouds that are not identical, we know that one EWF, so one Euclidean Weisfeiler-Leman, is going to yield different colorings for each of the graphs, right? And if I remind you earlier, what one EWF does, it looks at the neighbors of each of them, saves all of the distance information in a coloring of each node, and then defines a readout function that hashes this set of all of the coloring of the nodes. So if the two degree histograms are not identical, one EWL is going to distinguish point clouds. The interesting thing that we saw in our research is that even if the degree histograms are identical, so it means that after one iteration, one WL, the readout function yielded the same coloring histogram, and one EWL can still distinguish non-isomorphic inputs. Maybe it's a lot of words, but it will soon be very obvious. Okay, so here we see it less clearly. You don't see the image, but at home you see it. So on the right, we have 2 point clouds. One is differentiated by the other by just a reflection of the blue points. And these 2 point clouds have identical degree histograms, but they are not isomorphic. So you cannot have a global orthogonal action that takes one to the other. Yet we still, using one EWL, can distinguish these 2 point clouds. And we will show this in the next slide. We'll give a proof of that. Right, so the theorem says that after 2 iterations of one EWL, 2 point clouds receive the same color if and only if they are isomorphic. So why is this true? Even for the example we saw in the previous slide. So the first hidden state has all of the distance information. So each hidden state has the geometric degree of the ith node, just by definition of one EWL. And we assume that all of these geometric degrees are identical. So in the next iteration, what we have is actually, for each hidden state, we know the distance, for each neighbor hidden state, we know the distance from the origin hidden state. So each node has actually an ordered list of distances to its neighbor. Therefore, we can recover the complete distance matrix of the point cloud completely after only 2 iterations of one EWL. And like we said earlier, this distance matrix is a complete descriptor of the point cloud up to equations, permutations, and yes. Okay, so the question arises after we show that these models are in fact very expressive. Even if 2 point clouds have the same histogram, degree histogram, they can still differentiate 2 point clouds. And we want to ask, why would we need more expressive models? Why would we need models that can differentiate point clouds that these models cannot? So even if we have 2 point clouds that the model does not distinguish, and this is essentially the Lebesgue measure 0 set. It might seem trivial. The approximation of a continuous function on a compact set will be greatly harmed by this, even one point that is not approximated. So here we see 2 Gaussian distributions. And the blue one is the characterizes function, the one to approximate our model. And the red one is what our model will output if we identify these 2 inputs as identical. So it means that the model does not distinguish non-isomorphic inputs and can lead to a non-negligible effect on our approximation capabilities. So the question is, do there exist point clouds that message passing neural networks cannot distinguish, right? So we showed earlier that they distinguish a large set of point clouds, those point clouds that each 2 nodes have different geometric degree, but could there be counterexamples? So we tried researching it actually, and then some other researchers beat us to the results. And so these are 2-point clouds, and they're non-isomorphic, right? So this one has, if I rotate this by 180 degrees, I'm going to get the same point cloud. And if I rotate this one, I'm not going to get the same point cloud. So these 2-point clouds are non-isomorphic. Yet their distance matrices have identical geometric degrees for each node. So it's a little bit hard to see here in the class, but at home people will see it better. So on the left we see the distance matrices here. Each row in the distance matrix has exactly the same histograms of colors as the other rows, right? Each row has 2 reds, 2 kind of oranges, and 1 orange white color. So in terms of 1WL, when we run this test on each node sees exactly the same distances as the other nodes. So 1WL is not going to distinguish between these 2 graphs. It's going to output exactly the same readouts for these 2-point graphs, even though they're not isomorphic. Right? So we found 2-point clouds that are not isomorphic, that message passing neural networks cannot distinguish. Right. So how do we? The problem is, how do we distinguish these 2 point clouds? And what we found out is, if you look at higher order graph isomorphism testing, you can get a complete separation of the space of pointers. So what is this higher order KW graph? Rather than looking at each node and computing the coloring, we look at tuples of nodes. So at the KWL, we look at K tuples of nodes. And for each K tuple, you define the initial coloring. And then very similarly to the previous updating step in the 1WL, we update this coloring using its current coloring and coloring of its neighboring tuples. So what is the neighboring tuple in this case? Maybe I'll write it down on the board. This one. The notion of the neighborhood in this case is more intricate than just and each neighbor, if I have a K tuple I1, IK, its neighbor is any tuple such that we only change one of the indices. For example, for any J graph size, we just change the first index by J and leave all of the other indices identical. So each of these tuples are going to define as neighbors of the original I tuple. Right, so what I showed here is just one of the neighbors. The way it's aggregated here, right, is you actually get a tuple of all of these changes. For each J, we change each one of these. So the aggregation is different than the notion of the neighborhood. And in the aggregation, we look at each node and plug it into different neighborhoods, the tuple, and then update the color. Right. And then similarly to before, we just hash this set, the coloring. And this is a permutation invariant global graph feature. Yeah. It's essentially a classification of the graph. One-to-one classification of the graph. So people who know computer science know that this test is not complete for all graphs. For example, there do exist graphs that are not isomorphic, regular graphs, combinatorial graphs, that are not isomorphic, that this test does not distinguish. And so we don't really know if we apply this test onto a graph induced by point clouds, whether it will distinguish all such graphs. So we consider this question and we try to think about what K is sufficient for this iteration, meaning that any non-isomorphic point clouds, when feeding their induced Graham matrices into this algorithm, we get different hash. So this question was not answered in literature prior, and many people thought you had to run this test pretty much until infinity. There was no definite answer until for what K achieves complete separation. And do you have any guesses for what K achieves separation on point cloud? So I have a list of endpoints in R3. How many tuples, what size tuples do I need to consider to obtain complete separation when the input is in R3? For each, if the input is in RD, it's going to be different. We're only discussing R. Forest, okay. So the answer is actually 3. Yeah, 2 is not sufficient, but 3 is sufficient. I will show a rough sketch of the proof. And no, actually, wait, no. So it's a little bit more intricate. So 2 is sufficient if you consider 3 iterations. This was actually a result of people that built upon our work and published months after. But if you do only 1 iteration of WL test, the minima is 3. If you allow for a finite number of iterations, you can actually achieve it 2, even in R3. And okay, let's look at the sketch of the proof and to answer the question of why this is the case. Okay, so let's look at what information we have here. One update step of 3WL. Okay, so we have this set. We have all of these initial colorings that what we define, how we define the initial coloring is the Graham matrix of the graph defined by the I tuple. So we have a 3 by n point cloud. We only take the indices which correspond to this I tuple and compute their Graham matrix. So if I have the I1, I2, I3, the initial coloring C0 of I is going to be it's I1, it's I2, it's I3, transpose, times symmetries. Okay, and then all of these other neighboring colorings are just going to be to replace this xi1 with xj, right? So what I have is all of these Graham matrices, and I want to retrieve geometric information from them. Okay, so how do I do it? I iterate over all of these elements in the set, and I choose the one such that P0 of I is maximum. And I can do it in O to the N to the 3 computational time. And I take this rank of, and I take this C0I that's maximizing rank. You might have many of them, it doesn't matter, you just choose one. Right, and from algebra, we know the rank of this Graham matrix is identical to that of the 3 points that define what I wrote over there. So the rank of this coloring is identical to the rank of this matrix. It's very easy to show this fact. So now all that we need to do, we know that also from linear algebra, we know that if we work in R3, we have a basis for R3, and we have another vector, and we look at its projections onto the basis. These projections uniquely define the vector. So a slight modification that now we're not working on a basis for R3, but we have a basis for the point cloud. So these are three vectors that span the point cloud. And all we need to do is to extract the projection information from the neighboring coloring. But this is very easy, but the way that these neighborhoods are defined, if I look at, for example, I want to find J, I want to find xj, I want to recover xj from this information. So what do? I look at, I have C0 of I, when I replace the first index is J. What does this give me? It gives me exactly the same thing here. It gives me this thing here. Let's see, where's this? But here I now have xj, and then here I also have xj. And then if I look at the first row, this multiplication, I actually have the projection of xj on xi2 and xi3. And then if I replace j by the second one, so I have, now I have I1, j, I1, j. Then I have the projections in the first row. I have the projections of the second row actually of j on I1, I3. So I recover the projections on a local basis of each of the other vectors in the point cloud, and that's it. I'm done. I can recover each one of them once, and the basis I already know how to recover, right? So the basis, the 3 points that are a basis for the point cloud, I can recover very easily because the basis is defined by this tuple, right? So I have I1, I2, I2, and we've shown earlier this is the gray matrix of these 3 points. So I can recover these 3 points uniquely up to rotations and reflections. So I have a complete description of the point cloud. All right, but this is research that took a long time. This was a very fast explanation, but I hope you got something to it. Okay, so we thought about the result we got for the 3W plugins, and we said, how can we even further optimize it? And it turns out that if you use 2WL, you can also achieve complete separation by only embedding one more scalar of information. And so this scalar, essentially the determinant of xi, xj, xk, if you think about it. And this still achieves complete separation. It's a 2WL. Intuitively, when I described the proof earlier, we try to find 3 points that constitute the basis for the point cloud. But in fact, we don't need to sample points from the point cloud directly. We can just look at the cross product of 2 points and look at the triplet xi, xj, and the cross product, and this still constitutes the basis of the point cloud. So even with 2WL, with a very minute difference, we can still achieve complete separation. And we use this test in our practical implementation of the architecture. 7 minutes. Right, so we reduce the complexity to O to n squared and still achieve the separation. Okay, so now this was the theoretical part. Now we would like to simulate these graph isomorphism tests by neural networks. Why? Because they're expressive and we show that they can distinguish all the point clouds. And in literature in general, people are very interested in expressive models. Models work better, and this is why we want to implement these high-order KWL tests during neural networks. So all we need to do, we just need to define set embeddings that are injected, right? So when we define WL, we have this hash function that is one-to-one. And in a general case, it's very hard to define these functions using a neural network that will be one-to-one. So how do we do that? Right, so let's look at an early solution to this problem. So Segal et al. In, I think it was 2021, they showed that you do have complete descriptors of point clouds up to permutation by looking at their what's called a multi-symmetric power sample number. What does this mean? Yeah, given 2 point clouds, we can identify them up to permutation. Only working permutations now by looking at these polynomials. So how are these defined? And what we do is we do summation element-wise. So xi is in R3. And we iterate over all of the multi-indices of points such that the sum of the multi-indices is less than n. And we just look at a huge vector of all of these element-wise multiplications. And we get this n to the 3 long vector. And this constitutes a complete description of point clouds up to permutation. So these are injective embed functions. Right, so I said earlier, point clouds are just sets of points. These are also, when we're embedding sets, we're just embedding sets. But just disposing of your orthogonal. How do we improve this? We want to decrease the embedding dimension of these tower sample meanings. What can we do? We can actually just sample them. Signal reconstruction. We can take this huge vector px. This vector is n plus 3 in our case, choose 3, it's a huge vector, and just project it 6n times onto 6n unique vectors. And we know from signal reconstruction that these projections are going to be an embedding of this huge vector. So what's the problem with this approach? Is that we first have to compute this huge vector of polynomial, and then only project. So even though our final embedding is low dimensional, it's only 6n dimensional, the actual computational resources required are of order of n to the 3, which are a lot. If we want to simulate the WL test, it will just grow exponentially and be infinite. And so how do we remedy this? We do this by a process called polarization. What does this mean? We consider the one-dimensional permutation invariant embedding, and then we just project our sets onto one dimension, apply this embedding many times, and then obtain some one-to-one hash. What does this look like? So we have permutation invariant embeddings in Rn. They're very simple functions. So the sorting function, which is a piecewise linear function in Rn completely embeds a vector up to permutation. Right? The vectors that are the same up to permutations. This is going to yield the same vector here after sorting. If they're not identical, it's going to yield different vectors. But there are also the one-dimensional power sum polynomials that are also separating. Separating invariance means it's injective. So these two things both give us the same desired one-dimensional embedding. So then what do? We receive a point cloud in R3 times. And we take this point cloud, we multiply each one of the columns by some vector. This gives us just a vector in Rn. We feed this vector into one of these embeddings, and then take another projection just to reduce the size. And by signal reconstruction, we know that we don't need a lot of these vectors. We only need 6 and actually not 6 and yeah, we only need 6n plus 1. So it's supposed to be 6. You only need to have 6n plus 1 vectors to obtain complete separation. So what's the computational load that we have now? So earlier it was O(n) to the 3. Sorting is widely known to be the complexity of n log n. And we have to compute sorting for 6n plus 1 vectors. We have also O(n) number of variants. So we have a total complexity of n squared log n rather than O of n to the third. Right. And log is it's not a constant, but it's a very small quantity compared to just a linear function. So this is a very big improvement. And this is the result that my advisor did. But we applied this in our setting for the half function of the readout. So when we have the KWL test, we have the readout function. You have to iterate over all n to the 3 colorings, right? So naively, you need n to the 3 to the power of 3 size vector. But what we actually showed is that you don't need to consider each step in the process independently. And you can consider only the dimensionality of the input data. So even if we have a set of O to the n4 elements, O to the n3 elements, we only need to have 6n plus 1 vectors in order to define the injective set mapping of the final readout function. And yeah, and then we, at the final stage, yeah, I'm going to be done in a few minutes, is half an hour. Okay, no, so I'm going to finish this. So theoretically, this is true. We only need 6n plus 1 projections, but no one actually tested this before. So we did some experiments. We implemented a simulation of the 3WL test. Actually, this one, not 3WL, 2WL, which is correct. And we used only 6n plus 1 dimensional embedding, like not O to the n4, something crazy. And we still obtained scores on point cloud that one of these point clouds is a difficult point cloud that I showed earlier, of these two non-isomorphic point clouds that one EWL cannot distinguish, right? So our network, we've shown it to be complete. And on another note, other networks, these network maze and TFN, these are not message pattern neural networks. These are very expressive models but they're also very computationally large models. And these look at Hordan coefficients and crazy stuff in computation theory, and they also separate these examples. And another model, which is not message passing, but also relies on projections and gets kind of mixed. And right, and then furthermore, we showed that earlier when we said that message passing neural networks can distinguish point clouds if all of their even if their degree histograms are identical, but their geometric degree is unique for each node after 2 iterations. We also put that to the test, and this also turns out to be true. And that's another contribution. And okay, so now we showed this kind of theoretical work, and then we showed some experiments that kind of contrived, picked some point clouds. These point clouds don't really represent anything in real life. These are not like binaries or anything. They're just point clouds. And we showed that they separate. So we tried to also look at the molecular prediction that I said earlier. So what people here see, we don't see the left of this table, but the top one is the result of message passing neural networks. And the bottom row is the result of R neural network. And we see that in some cases we do worse, but there are most of the time we do slightly better. And in some cases, like in alpha, in delta epsilon, we get like a 4 or 5% improvement. And so yeah, so this is kind of it depends who you talk to. Some people think it's very slight. Some people think it's good. Anyway, we've shown some indication that more expressivity in this network works well, but there's definitely room for future work in improving the practical application of the model of the simulation of the Weisfeiler-Leman. And yes, that's pretty much it for this talk. Yeah, we finished the thoughts. So thank you. And if you have any questions, there are any questions?
You define expressivity?
Yes. Expressivity means that you get some input from some domain. So in our case, our domain was R 3 times. And we put some symmetries, applied some symmetries onto this domain, right? So we have some equivalence class defined. So if you have some rotation and permutation that takes one of them. And then expressivity means is what the subset of the input set can you distinguish? So given 2 non-isomorphic inputs, am I injective on this subset, and how large this subset? So in our case, the subset was R 3 times N. We've shown constructions that are completely expressive, or maximally expressive, distinguish all non-isomorphic inputs. For example, another case is if you just look at regular graphs, you look at KWL. So in this hierarchy of KWLs, when you increase the K, you get a more expressive test. So there is a graph that KWL, and there are 2 graphs that KWL does not distinguish, but K plus 1 WL does distinguish. So in the context of graphs, it's just how many graphs can you distinguish. And in the actually context of graphs also, there is no known polynomial time of distinguishing algorithm for distinguishing all combinatorial graphs. Yeah, in the case of point cloud, interestingly, there is a polynomial time algorithm for comparing point clouds. So this result makes sense that we only need finite many Ks for KWF. If you could not have compared point clouds in polynomial time, this result cannot hold. So it means that.
Are there any more questions? Okay, so let's all thanks you again. And see you all in 2 weeks.
הערות שרדו בבית הבא.